Guys are always so talkative until I start talking. Okay, well, we're going to jump back in on Chapter 4 here material today, and starting here on page 5, bottom of page 5 of your notes. So here in Chapter 4, remember, we're talking about continuous random variables. Chapter 3, we talked about discrete, where the random variable takes on a finite or countably infinite number of values. Here in Chapter 4, things are taking on the range of sort of an interval or a range of values that's uncountably infinite. So we have to think about things in a slightly different way. We talked about the probability density function, the PDF, instead of the probability mass function. Remember that we looked at in Chapter 3. And we talked about how ideas of the CDF and expected value and variance translate to this context. And then here we're going to pick up a little bit. What we'll talk about more in section 4.3 and beyond is sort of like we did in the later part of Chapter 3, where there's sort of certain types of random variables that we see often enough that have special names, and so we'll talk about those and the properties of those. And here's a sort of a simple example of sort of the first official distribution that we'll talk about here in Chapter 4. So this thing is called the uniform distribution, and it's very simple. Our random variable x is going to have this distribution if it's kind of any value in that range from a to b is equally likely. So the PDF of x is going to be is actually just going to be a constant. So there's no x floating around in there, right? So it doesn't depend. The PDF doesn't depend on what the value of x is. It's going to be a flat constant value. So when x is between a and b, it has that flat constant value, and it's 0 otherwise. And then our notation here will be that x is distributed as a uniform random variable, and that in the brackets we have the endpoints. So a and b are in there. And so some pictures here for you, more lovely diagrams from your textbook. In the upper left corner there, this is the PDF. So it's 0 outside a and b, and then it kind of jumps up to this constant value in between a and b, and then is back down to 0. For values of x outside that range. And then of course the area in that little square has to equal 1, so that means the height of that thing is at 1 over b minus a. We can talk about areas in the same way that we did before. Remember in Chapter 4, probability corresponds to area, so we're finding a certain area under the curve for probabilities. And then down here is the CDF. So it's still a continuous function, has a little less smoothness, but it's continuous, unlike we saw in Chapter 3, where there's step functions. But the CDF is 0 until you get to A, then it increases linearly up to 1 when you get to B. So again, this is kind of the uniform distribution is something that you'll see sometimes, and we can talk about some properties of this distribution. Okay, so first thing. Now that we've shown you a picture of the PDF and the CDF, the next thing we always talk about, of course, is the mean and the variance. And again, we have formulas for these things. So for a uniform random variable, its mean is going to be expected value of x up here is going to be a plus b over 2, and its variance is going to be that thing listed there, b minus a squared over 12. And so want to quickly derive the mean, and I'll leave it up to you guys to think about how to calculate the variance. Okay, so again, by definition, the expected value of x is the integral member now over all numbers of x times the PDF f of x. So that's just by definition again. And now we can chop down those endpoints of integration based on the positive probability that we have. So it actually just goes from a up to b, x, and then the PDF is just 1 over b minus a. So just filling in what each of these things are here. And that's a nice simple integration to do. So this is just 1 over b minus a times x squared over 2 evaluated at a and b. And so that's b squared minus a squared over 2 times b minus a. And if we do some algebra here, this is b minus a times b plus a. So then some things cancel there, and we get exactly what we hoped we would. And that should make sense. So we're talking about just a rectangle here is the shape of the, if you think about the PDF as sort of a solid shape. Remember the mean is the balancing point of the distribution, right? So it should be, if our PDF here is kind of this rectangular shape, it should balance there right in the middle. So right in between A and B. So this point here is A plus B over 2. So that's just the midpoint of that distribution, right smack in the middle. So that's the expected value, and then the variance, again, to calculate that, you probably want to use a little trick that we came up with. But can be done fairly straightforwardly to find that the variance is that other thing there. So I'll leave that up to you, but we're going to just use that fact now moving forward. Okay, so then more formally, just kind of say one more time what the CDF is here. Here's a formula for what it is. Again, it's 0. If x is less than a, it kind of has that nice linear shape between a and b, and then it gets to 1 when you get to b and stays there on out. So that is the CDF, which we can also use moving forward. Okay, well let's do a little example here. Practice using some of these things. And here in this example, we'll let x equal the amount of time it takes to read or write on a certain computer disk memory device. And I'm going to make some assumptions. So the disks rotate once every 25 milliseconds. So a reasonable assumption that is it's going to be uniformly distributed. The amount of time it takes is going to be uniformly distributed from 0 to 25. So including the endpoints there. And so again, our picture here, practice drawing the PDF here. This is f of x. Down here is x. So from 0 up to 25, we're just going to have this nice flat shape, and it kind of is 0 otherwise. And then what's the height? What's the height of that rectangle? Yeah, exactly. 1 over 25. So 1 over b minus a, again, you can just also think we need that area under that thing to add up to 1, so the height has to be 1 over 25. Right there. Okay, so first question here. Compute the probability that x is between 10 and 20. So I think when it's easy anyway to draw out a picture of the PDF, that kind of helps us. That helps me anyway see exactly what we're looking at. So if here's my PDF, I want the probability that x is between, say, 10 and 20. So I want to know what the area of that shaded in space right there is. This is CDF, PMF, PDF, and this is the values there. Okay, so I think you could probably all see how to very quickly, you could formally set up an integral there to calculate that area, or you could just say, well, the height is 1 over 25 and the width is 10, so calculate it that way. Just for fun, I'll practice using the CDF just to kind of remind us how that works. So the probability that x is between 10 and 20. How can I use the CDF to find that value? Yeah.
Probably that x is less than 20, subtract off less than or 10 in this case.
Yeah, right. So So again, we can take the probability that x is less than or equal to 20. And you want to subtract off then, like Jim said, you want to subtract off, well, you could subtract off the probability that x is less than 10, maybe to be technical there. But what's the probability that x equals 10 exactly? 0, right? The probability for a continuous random variable, the probability of being exactly equal to a particular value is 0. So we can leave the less than or equal to sign in there, and that's totally fine. So, so with making the jump from that, that's kind of what we're looking for. Well, that's just the CDF of 20 minus the CDF f of 10. And then, so again, we know what our formula for the CDF is. That's x minus a, which is 0, divided by b minus a, so 25 minus 0. That'll just be 15 over 25. Sorry. (10 over 25), or 2/5. So again, if you can draw that picture and realize that you're just calculating the area of a rectangle there and do it that way, that's totally fine. Kind of practicing using the CDF there. Okay. Similarly, we can calculate the probability that x is bigger than 10. Again, you could use the same picture there, and realize you're just calculating a rectangle, so you could do it that way. Again, practice using the CDF to calculate this thing. How could I use the CDF to calculate this? Yeah.
1 minus half of 10.
Exactly right. So this is 1 minus probability that x is less than 10, again, which is 1 minus the CDF f evaluated at 10, which is just 1 minus 10/25, which is 0.6. Okay, pretty straightforward. Let's again just practice out writing what the CDF is here. Again, we can just use the formula that we had that's just above there on your notes. So the CDF again is 0 if x is less than a, it's 1 if x is bigger than b. And in the middle we have again x, sorry. I want to actually use the numbers that we have here. So if x is less than 0 and 25, sorry about that. So we have x minus 0 over 25 minus 0, or just x over 25 if x is between a and b. I can't stop writing a and b here, can I? Have trouble on these Monday mornings sometimes. Okay, so just again, this is very simple. Maybe stepping through writing out the CDF, but again, just remember we do define the CDF for all values of x. So from negative infinity up to positive infinity, this thing has been defined. It's 0 and 1 for most of that time, but just if you're ever asked to write down the CDF, make sure to do it like this and give the CDF for all possible values there. That's just good practice. Okay, and finally we can talk about the mean and standard deviation of our random variable x. So if it's uniform 0, 25, its expected value, again remember, is a plus b over 2, which here is just 25 over 2. Right there in the middle, 20 at 12.5, and the variance again is b minus a squared over 12, 25 squared over 12, which is about 52.8083. So if that's the variance, what's the standard deviation? Square root of that, right? So then the standard deviation of x, you can remember that's the square root of the variance of x, or the square root of 52.083, which is about 7.217. So again, this is kind of a simple example, but it starts to highlight it's a good idea to memorize what the mean and variance of these things are. So you did that. You probably did that already with the binomial distribution and the Poisson. Those are a little straightforward too, but you can save I mean, you could derive this obviously each time, or you could just memorize that what the expected value is and use it that way. That's totally fine. Is everybody on board with me here? Can you guys think of any questions on this example? We all good? Okay, well that is the uniform distribution, and we'll come back and later in section 4.3 and beyond we'll talk about some more sort of distributions that have names and properties that we'll look at more than once. Okay, so the last thing to talk about here in this section before we get to 4.3 is this idea of percentiles. So I'm sure you've all heard the percentiles before. Let's kind of formally define what these things are and talk about how to calculate them here in chapter 4. So for a number between 0 and 1, we're going to use our favorite letter lowercase p there again. The 100 times pth percentile of the distribution, so if you want the 99th percentile or something like that, p would be 0.99 of the distribution is defined in this way, and we're going to denote it by this function eta of p. So again, it's just the probability. We want the percentile to be such that the probability of being less than that is equal to this percentile. So for whatever number we're looking at there, the probability of being less than that is equal to the percentile that we want, which of course is also just the CDF evaluated at that point. And in our sort of general terms there, that the CDF again is just that integral, so we can set up, take our PDF and integrate all the area up to eta of p such that it gives us the right percentile there. So again, kind of a little picture to help motivate this is if you want the shaded area under here to be equal to some value, let's say 65% or 0.65, then I just need to find the eta value there of that gives me that correct shaded area. And you can also think about it in terms of the CDF. Again, my p can range between 0 and 1, and so whatever percentile I want, I can just find that point on my CDF and trace over and figure out what value on the x-axis that gives me. So this is kind of our very formal way of defining percentiles. And a very special percentile that we'll talk about more than others maybe is the median. So you guys have all heard the median before, I think, yes. Again, that's just the 50th percentile. So it's the number that's right in the middle of the distribution. And sort of thinking about it in terms of our notation here so far, the median is going to be such that the probability of being less than that is equal to is 0.5. So it's kind of 50% of the distribution is below it, and 50% of the distribution is above it. So you could find the median of a distribution in this way. And then just to note that if we do have a symmetric distribution or something that's kind of has a nice reflection point somewhere, the mean and the median will actually be exactly the same. Yes, so that could be a little shortcut there too, if you have a distribution that is symmetric. Okay, so let's look at an example on how we can go about calculating the median here using this formula. So we already looked at this example earlier in this chapter where we had a particular PDF as such. So between 3 and 5 it had this linear form and it was 0 otherwise. And then we found its CDF. We also calculated that thing out in an earlier example here. And so the question we can now go about answering is what is the median of this distribution? Well, again, the median is just the value that gives you 50% probability of being below that value. So again, we want to find the value of mu tilde. So this is mu tilde. We want to find that value such that the CDF is equal to 0.5. So this is pretty straightforward since we have the form of the CDF already. So whatever that mu tilde value is, you can write out what the CDF is. It's just 0.035 times that value squared plus 0.2 mu tilde minus 0.9375. And if you move some things around there, you can get this to be 0.0375 plus 0.2 mu tilde minus 1.4375 and set that equal to 0. So either one of those is the same thing. I'm just moving some things around there. And now we're going to have to remember our algebra knowledge and see that we have a quadratic equation here, and we just need to find the roots of that equation. So again, so therefore mu tilde is going to be equal to either negative 0.2 plus or minus 0.2 squared minus 4ac, right? So minus 4 times 0.0375 times negative 1.4375. Well, that's under the square root. Divided by 2 times a, so 0.0375. And so that's negative 0.2 plus or minus 0.5056 divided by 0.0751. So that's the same as this is equal to either negative 9.4 or 4.075. So it's one of those two things. So which one is the median then? Why is 4.075 the median? Exactly right. So again, remember our distribution has to be between 3 and 5, so we can pick out the positive value there. So actually 9.4 is not it, so mu tilde is equal to 4.075. That's your median of this distribution. And then you can go back and just double check that does, so take F, so you can check that the CDF evaluated at 4.075 does indeed equal 0.5, or pretty close anyway. Okay, questions on percentiles or finding this stuff? Okay, well I wanted to do, before we move on to the next section, I wanted to insert an extra example here to maybe take it slightly beyond what we've talked about in the notes so far. So this is not in your notes. Take a quick detour from the notes. So another example of a continuous random variable here. So this is again something we won't officially talk about in this class, but it's something that you might see it sometime in your future studies. So this is a PDF that can be used to approximate certain things that are positive. So it can approximate the distribution of income or a city population or something like that. And it's as follows. So f of x, and I'm also throwing a theta in there now, is equal to 3 theta cubed over x to the fourth if x is bigger than theta, bigger than or equal to theta, and 0 otherwise. So kind of like, well, again, we'll see this more later. But for these distributions, you can often throw in a parameter and make that whatever you want it to be, and this thing is okay as long as theta is bigger than 0. So the PDF here depends on a particular value of theta in doing the calculations here. And so this is called a Pareto distribution, and the theta parameter here represents some sort of a minimum possible income or population or whatever we're talking about. So it's whatever you're trying to approximate here, that's the minimum value that's possible. So just make a note here that theta is a parameter, which we'll again talk about more later. But again, you can make that whatever you want as long as it's positive, and this thing does work out. Okay. So anyway, taking this as our PDF, we want to kind of go through our usual calculation that we've done here. We want to verify that this thing is indeed a valid PDF. So again, I just need to integrate this thing over all real numbers, negative infinity to positive infinity. And what am I checking to see if this is equal to? Somebody in the back, what do I want to see if this is equal to? Excluding the table row. So what do I need what do I need the area under the curve, the whole curve, to be equal to? Yeah, so we just need to make sure that that is indeed equal to 1. That's our properties of so the PDF is always positive. I guess you could sort of formally check that as well. But we need the area, need to integrate the whole thing to be equal to 1, so plug this thing in. So again, it's only positive when x is bigger than theta, so we can go from theta up to infinity of 3 theta cubed over x to the fourth. And so this is 3 theta cubed times negative x to the negative 3 over 3, evaluated at theta and infinity. So 3's cancel out here, and this is negative theta cubed, evaluated at theta and infinity, which is negative 0 plus theta cubed over theta cubed, which is indeed equal to 1. It's good practice of our integrals here. So infinity to the negative third power is 0, and yeah. So we're good. So our this is a valid PDF. It's always positive, and it integrates to 1, and so we're good to go. Okay. So if we have a random variable x that has this PDF for some generic b, some value b that's bigger than theta, we want to give a general expression for being less than or equal to that value. So again, just by definition, the probability of being less than or equal to b is just an integral from theta up to b of the PDF. So, 3 theta cubed over x to the fourth dx. So kind of the same thing as we just saw before. This is 3 theta cubed times negative x cubed over 3, except evaluated now at theta and b. And again, so we get theta theta cubed times negative 1 over b cubed plus 1 over theta cubed, which is 1 minus theta cubed over b cubed. Everybody following me here? We all good here? Okay. Next, suppose now that theta is equal to 100. So however we got there, we're just going to assume that theta is equal to 100. What is the probability that x is more than 200? So now this is the probability that x is bigger than 200. And of course, well, there's a number of ways that you could calculate that. But maybe the best way, since we know what we just calculated on the previous page, that's 1 minus the probability of being less than 200, less than or equal to. And you could calculate that however you like, or we can just use what we found before. So 1 minus, again, 1 minus theta is now 100, so 100 cubed over 200 cubed. So remember the probability of x less than or equal to b was 1 minus, here theta is 100. And this is just 1/2 cubed, or 1/8. So again, ones cancel out here and simplify there. Okay. Let's calculate what the expected value here of this thing is. Practice how to do that. So again, the expected value of x, negative infinity up to positive infinity of x times the PDF. Again, this is now just theta up to infinity of x times 3 theta cubed over x to the 4th. And this is a nice, fairly straightforward integral that we can do. The x in the numerator cancels one of the x's in the denominator. So this is theta to infinity of 3 theta cubed over x cubed. Again, 3 theta cubed times negative x squared over 2, evaluated at theta and infinity. And this is 3 theta cubed. Again, plug in infinity, you get a 0. Plug in theta, you get 1 over 2 theta squared. So this is equal to 3 theta divided by 2. So I guess are you guys okay with the fact that there's a theta floating around in there? So it's kind of like with the binomial PDF or PMF. Yeah.
X to the negative 2.
Thank you. Thank you, Jamie. So like with the binomial PMF, you had your expected value. We calculated that in terms of p, right? So for whatever the success probability was, we could do the general calculation, and then for a specific example, we could say, oh, if p is equal to 0.5, then we can throw that in there and use that in what the expected value is. Same kind of an idea here, kind of generalizing it. So if theta was equal to 100, like we had in the previous part, the expected value would have been, 150. So this is just a way to generally do these calculations, and then for a particular example with your theta equal to whatever, you can just throw it in there. So kind of like what we saw back with the binomial distribution. Okay, and final question for you here. Again, so let's now say again that theta is equal to 100. If we're assuming x is bigger than 200, what is the probability that x is bigger than 300? So a little more complicated here. Again, I want a probability. What do I want the probability of here? Say again?
X between 200 and 300.
So the probability that x is between 200 and 300?
Oh.
So it's very, very close, right?
X is greater than 300 given X is greater than 200.
Okay, yes, exactly. So again, if I'm assuming x is bigger than 200, it's kind of like going back to our idea of conditional probability. So I'm going to assume that x is bigger than 200, and then I want to answer some other probability question. So what I want is the probability of x being bigger than 300, given that x is bigger than 200. So again, did everyone see how we got that? So I'm assuming, or I'm conditioning on x being bigger than 200, or given that x is bigger than 200, all that language is the same. Given that x is bigger than 200, what's the probability that it's bigger than 300? Everybody okay with that? Okay, so again, it's maybe not immediately obvious how to get there, but we can. A good strategy is always your general rules. So it's kind of like you have two events here. It's like our A, and this is like our B. So probability of A given B. You all remember what that is? Who can help me out with that one? So the probability of A given B is equal to what? Yeah.
A union B over B.
Probability of A union B over the probability of B.
No, not union.
Not the union.
It's,
It's the other one, right? A intersect B, right? So the probability of A given B is probability of A and B, A intersect B, over the probability of B. So now we can just use that and write this out. So this is the probability of x bigger than 300 intersect x bigger than 200 divided by the probability that x is bigger than 200. Okay, so we're getting closer to something that we know how to calculate, but we still don't quite know what to do with the numerator up there. What can I do to simplify that? So what's the intersection of x bigger than 300 and x bigger than 200? Yeah, right. So if I want all the cases of where both of those things are satisfied, that's just going to be x bigger than 300. So this is equal to the probability that x is bigger than 300 divided by the probability that x is bigger than 200. Everybody okay there? Take your side. Yes. We okay there? Is everyone okay? All right. So again, now we can. We already found the denominator. That was 1/8, I believe. The numerator we could find similarly. So this is 1 minus probability of being less than 300, which is 1 minus 100 cubed over 300 cubed divided by 1/8. And that's just 1/3 cubed over 1/8, or 8 divided by 27. questions or comments you guys can think of on this example? You okay? All right. So that's the end of my extra example here. I know we're a little ahead of schedule here, but I think I might call it quits here with one, as long as you guys do one thing for me. So I wanted to take a few minutes here, since we have a little time, to get some feedback from you guys on how the course is going. So if you would, in the next 3 to 5 minutes, take a little half sheet of paper or whatever, scrap sheet of paper. Please don't put your name on it. And just write down kind of how things are going. Please be honest. I'd be interested in knowing, specifically I'd be interested in knowing how the pace of the class is going, if it's too fast, too slow, what you think of my teaching, if there's anything I could be doing to improve, let me have it. So thank you guys very much. And again, please don't put your name on it unless you want to, I guess, and then bring it up to the front when you have that all done. So thank you very much in advance.